Okay, let's introduce queuing theory. Queuing theory is the study of waiting. It gets its name from waiting in line. Not the most common term here in the U.S. to call a line a queue, but especially over in Britain, you'd call standing in line is queuing up. Um, uh, but queuing theory is not just limited to people waiting in physical lines, but has tons of applications of anytime something is waiting for something. And so it could be trucks or ships waiting to be unloaded at a port or an unloading facility, airplanes waiting to take off and land, digital transmissions waiting to be processed. And so yeah, inside your network system where you're kind of sending and exchanging messages, those have to be kind of queued up and processed. Manufacturing parts waiting for the next stage in their processing. And so you can actually, in manufacturing, end up with a queuing network where you have sort of different queues or waiting times along the process from the beginning to the end. And each of these can be described as a queuing system. And so queuing theory, pretty useful area of operations research, builds off of the previous stuff that we've been talking about with simulations because it's definitely a stochastic system that evolves by chance over time. And so one of the best techniques you can use to deal with a queuing problem is to simulate it. So some things of kind of definitions for the structure of a queuing system is we've got some sort of input source. Um, this can be kind of trucks coming in. This could be airplanes. So whatever your population of objects that will be waiting, they come from some input source. Okay. This could be finite or infinite. If it's suitably large, we usually assume it to be infinite. And then the items or things that will be waiting, we call them customers, even if they're not actually customers at a store. Just kind of the standard literature is to call those customers, even if they're ships or parts or whatever else. Um, and we assume that they arrive according to a random process. The most common assumption is that the time between arrivals of customers is an exponential distribution, and I'll have a special video just on the exponential distribution and some of its interesting properties. Though other distributions could be used. You could just have items that arrive at fixed intervals. Pretty unusual to have kind of that nice fixed interval, but it's possible. Then the queue is where the customers wait before being served. Um, the queue can have some maximum length, either a hard constraint on the physical space and that there's not room for another person in the queue or another um, truck on the lot or another digital transmission, or just the fact that if your queue is too long, people are going to leave. Like the times that I've visited the DMV and noticed that the line was out the door, I'm like, well, I'll come back another day, and hopefully it won't be this busy because I just don't want to wait. And then the rule for which you decide the order that members in the queue are selected to be served is called the queue discipline. For most analysis, we'll assume that this is just first come, first serve. And then you've got some mechanism of serving the customers. Your service mechanism can consist of one or more servers, and so you can kind of have parallel service channels. And the time that it takes to complete that service is usually a random variable. So it might be a fixed amount of time, but oftentimes we'll model it as a random amount of time to complete the service. And so you might think of people at the DMV, everybody comes in with a slightly different request that takes a slightly different amount of time. And so you can use a random variable to represent that random amount. Most common random variable for service times as well as arrival times is an exponential distribution, mostly because it does a pretty good job matching up with reality, but it also is easier to deal with as far as kind of looking at things analytically, and you can actually solve some stuff out if you use exponential distributions. We often write the system in terms of the three most important pieces of information: the inner arrival times, the service times, and the number of servers. And so one common model is what's called MM1, which means that the arrival times or the inner arrival times are Markovian, which is another word for exponential. The service times are Markovian, also exponential. And in this case, there'd be one server. And so your book has a whole section on the MM1 model where both arrival and service times are exponential and there's one server. That's probably the simplest case to deal with analytically. But you can have other distributions for arrival and service times. They could be degenerate, which means that they're constant. Maybe more common for service times where everybody needs the same thing done. And so it's a constant amount of time for service. Erlang is another word for the gamma distribution that you see used. And it's equivalent to the sum of a bunch of exponentially distributed variables. And so if you have to wait until a batch comes in, so you can have kind of inner arrival times that are exponentially distributed, but if you're only going to process things in batches, that's where the gamma or Erlang distribution will often play in. And then G would stand for any general distribution that you might be interested in. So you could use a normal distribution or something else, though there's sort of some reasons why you might not want to use a normal distribution for inner arrival times or service times, because we need that those times have to be positive numbers. And if you know a little bit about the normal distribution, it has some probability even on negative numbers. Now, there's ways of maybe fixing that, but most of the time you're using a exponential or also known as Markovian distribution or an Erlang distribution. So you've got your system. What are some of the important metrics of your queuing system? These are the things that you're interested in measuring about your queuing system. And then oftentimes some of these you might have control over. And so then you tweak them and see how the other metrics respond. Okay. And the book has sort of common symbols throughout this chapter. And so these are the symbols that your book uses for each of the parts of the system. So S is going to be the number of servers and the number of parallel service channels. More servers usually means that you can serve more people simultaneously and kind of keep your queue length shorter if you have more servers. N of T, that's going to be the state of the system, essentially how many customers are in the system at a given time. Okay. And then P sub n of T is the probability of exactly n customers in the system at a given time. And so where n of T is sort of tracks the state throughout, P of n of T sort of takes a step back and looks at what's the probability of there being this many customers in the system at a given time. Lambda is the mean arrival rate. It can potentially depend on how many customers there are in the system. So usually it doesn't. Usually it's just a constant, and then we'll just write it as just lambda without the n. Mu sub n is the mean service rate, which is the expected number of customers served per unit time. And so you might serve three customers per hour, and so you'd have a rate of 3, or you might serve 2 every 1 hour, so your rate would be a half, or that'd be like half a person per hour, half a customer per hour. And then, and that's sort of the overall aggregate for all your servers. And then mu is the service rate for a single server. And so if we think about, if we've got S servers, let's say 3 servers, mu sub n is going to be equal to S times mu if our servers are all in service and we have a queue. On the other hand, if not all of our servers are in service, Then our mu sub n is going to be however many people are in service times mu. Okay, so yeah, usually your mu sub n is sort of 0 if nobody's being served, 1 times mu if one person's being served, 2 times mu if 2 people are being served, 3 times mu if 3 people are being served. But then if you only have 3 servers, then if you have a 4th person, your service rate is still 3 mu. And same for 5 people or 6 people. If you only have 3 servers, then you have kind of a service rate of 3 times mu whenever everybody's full. Rho is an important metric that is called the utilization factor. Essentially, it's the fraction of time that each individual server is busy. If you get to a utilization factor of 1, then everybody's busy all the time, and your queue is going to be growing, unless there's some sort of relief valve or some reason that people just leave the queue. If lambda and mu are constants, then your utilization factor is the rate at which people arrive divided by the rate at which people are being served. And so it's this lambda over S times mu. And so we'll see this utilization factor again later on. And then kind of some Q characteristics. L is the expected number of customers in the system. LQ is the number of customers in the queue, excluding those being served. W of T is the expected wait time, including the service time, and WQ is the wait time in queue, excluding the service time. Okay, and so if you think about what your goals might be, your goals might be to limit the number of customers in the queue or the number of customers in the system overall. You might want to limit the amount of wait time or the amount of wait time just in the queue. And so depending on the scenario, each of these might in some way be the objective where you're trying to minimize one of those to reduce your costs. Okay. One other thing to kind of think about and be careful about when you're thinking about queuing systems is transient versus steady state. So at the beginning, when you start up a queuing system, it's going to depend on that initial state that you started with. And so if you think of a typical maybe customer service type role, at the beginning of your shift, right, assuming that like the call center is just opening, there's nobody on the lines, there's nobody waiting to be served. But then, and so that's going to influence sort of the number of people in the queue and in the system for the next maybe 10, 15, 30 minutes of your shift. But after the first 30 minutes or an hour, then if I were to peek in an hour later and 2 hours later, the probability of having a certain number of people in the queue would be indistinguishable. And so that's what we call reaching steady state, where the kind of state of the system is no longer really related to the initial state at all. And the probability distribution of having any number of customers in the system is the same and doesn't depend on time. Okay. Most of the theoretical results are for steady state and sort of assume that the queue has been running for a certain amount of time. If you want to try to analyze transient cases, it tends to be pretty messy. But the nice thing about simulations is that it can handle both transients and steady state and kind of simulate a realistic scenario. And I'll say transients, kind of startup time is really important if the characteristics of the queue change throughout. And then in that case, the system may never reach steady state. And so if you want to try to model something where maybe you're looking at customers coming into your store, you might want to model the arrival time as being different through different parts of the day. And so if you're saying that the arrival time is 2 per hour from 10 to 11, but then 2.5 per hour from 11 to noon, you can't really use the steady state results because your system never really reaches steady states. It's sort of every time you change the parameters of the queuing system, the system kind of picks up from a different state is maybe how I'll see it there. But nice thing is that simulation can account for that, and you can build that into your simulation model. And so I encourage you to read through the chapter, and I'll present some of the sort of theoretical results in a later video. But we're mostly going to focus on how do we simulate queuing systems, and that's going to be the focus of the next video.